30 times further from the sun than Earth sits a world plunged in perpetual twilight. Out here, the baseline temperature hovers at a staggering -373 degrees Fahrenheit. At that extreme distance, solar radiation is incredibly weak. Thermodynamics suggests a planet in this environment should be a quiet, static block of ice and gas, with an atmosphere effectively frozen in place. When Voyager 2 arrived in 1989, its sensors recorded data that contradicted our basic theories of how outer planets behave. Instead of a dead world, Voyager revealed an atmosphere of constant motion. It captured towering white methane clouds swirling above massive storm systems, including a churning vortex the size of Earth, known as the Great Dark Spot. The telemetry data showed these atmospheric currents moving at speeds that defy their distance from the sun. Winds on Neptune travel between 1,100 and 1,500 miles per hour, supersonic velocities that make it the windiest planet in our solar system. The chaos extended to its largest moon, Triton. Despite surface temperatures approaching absolute zero, the crust is scarred with dark streaks, the result of active geysers firing plumes of ice and dust 8 kilometers into the sky. If the sun is too distant to drive this kind of massive weather system, an unseen engine has to be powering the violent chaos of the Neptune system. To find that power source, we first look at what the planet is made of. It's mostly hydrogen and helium, but it contains trace amounts of methane gas. Methane absorbs red and infrared light, which reflects back the deep, vivid blue hue we see here. But it's the infrared data that reveals a massive planetary energy anomaly. Neptune actually radiates 2.4 times as much energy into space as it receives from the sun, fueled by a hidden internal heat source radiating from its core. For decades, scientists debated whether this escaping heat churned the entire mass of the planet or just the surface. By analyzing slight variations in the planet's gravitational field, researchers could finally map exactly how deep those supersonic winds penetrate. This cross-section reveals a surprising divide. The bottom 90 degrees rotation, and its gravity is so weak that its thin nitrogen atmosphere bleeds 800 kilometers out into space. Unlike Neptune, Triton doesn't have a massive internal heat engine. Its activity relies entirely on a relationship with the distant sun, experiencing extreme seasonal cycles that last for centuries. When Triton's southern hemisphere entered its summer solstice in 2001, scientists observed a microscopic increase in temperature. That tiny warming trend was enough to trigger sublimation, turning the solid nitrogen ice on the surface directly into gas. As that nitrogen gas expands, deflected by the moon's rotation, it generates massive surface winds. These winds sweep across the crust, picking up dark hydrocarbon dust. Below the crust, this heating creates intense pressure pockets. The result is cryovolcanism, massive plumes of icy gas and dark material violently erupting through the surface. Even at the outer edges of the solar system, a microscopic influx of solar energy can trigger a violent geological and atmospheric engine on an otherwise frozen rock. Neptune and Triton show us that ice giants are incredibly efficient systems. They can take trace amounts of energy, whether from a cooling core or a distant star, and convert it into extreme weather and geological activity. Understanding how these engines work is crucial, because we now know ice giants are one of the most common types of exoplanets in the entire universe. Since 1989, our entire understanding of how ice giants evolve has been built on a few hours of flyby telemetry. We are currently extrapolating the physics of an entire class of planet from a single afternoon's worth of data. To fix that, scientists are designing the next generation of deep space missions. Projects like Neptune Odyssey and Triton aim to launch in the 2030s, placing a dedicated orbiter in the system and sending an atmospheric probe diving directly into Neptune's gas layer. These instruments are designed to precisely map the planet's gravitational harmonics, pierce that supersonic weather layer, and use magnetic induction to measure the saltiness of a potential liquid ocean hidden deep beneath Triton's ice. To understand the true mechanics of planetary evolution across the universe, we have to return to the dark, freezing engines waiting at the edge of our own solar system.